This video here should be hopefully a review, either from junior high or if we've done the POGIL. So looking at a bunch of stuff about matter. So maybe more of a review here. So matter, anything that has mass and takes up space. So mass, measure amount of stuff or material and object, and then volume is how we measure space. Don't worry about this weight and gravity thing. That's more of a physics concept. Alright, describing matter. We can describe matter in terms of its properties, and those properties then we can kind of subtype them as either extensive or intensive. E goes with A, so extensive goes with the amount of matter. So if I have a little bit, if I have a small pile, weighs a little bit. If I have a bigger pile of something, it would weigh a lot more. So mass is definitely extensive. Same thing with water. I could have 1 drop of water, and I would have a small volume. I could have 10 drops of water, and I would have a bigger volume. So volume, tends to deal with the amount. Calories, which stinks because I can't have my 18 bags of M&Ms. I can only have a few because calories keep adding the more and more you add. Intensive, though, is kind of the opposite, which is weird to think about. Intensive, I goes with T. So intensive deals with type of matter is present. So like chalk, very soft. No matter which piece of chalk you have, it's still going to have that same property. Doesn't matter how big or small that piece of chalk is. Same thing with like density. Pick any metal. Aluminum. If I have a little bit of aluminum or a lot of aluminum, it doesn't matter. The density stays the same. So the mass per unit volume doesn't change. Same thing with boiling point of water or any substance, but water. If I had a little cup of water, it still boils at 100 degrees Celsius. Whereas if I had a large container, a swimming pool, it's still going to boil at 100 degrees Celsius. So that point at which it boils doesn't change, and that deals with the type intensive properties there. So a bunch of other stuff about properties. So properties are words that describe matter. These are adjectives that we use compared to changes, which are different, and we'll talk about them here. Physical properties, these are something you can change without changing a material's composition. So if something is blue, when I look at it and say that it's blue, it doesn't change color. I'm not changing the fact that it's blue. Hardness, melting point, boiling point, I can measure water's boiling point at 100 degrees Celsius and I don't change anything about it. It still stays water. Chemical properties, these things can only be observed when that substance changes. So if I want to see if something burns, well, I have to light it on fire, and when I do that, and if it does burn, I change it from a piece of paper, I change it to carbon dioxide and water and ash. So the material does end up changing. It's no longer paper anymore. It is changed into something else. So there's some other examples there. I would definitely make sure you write those down. Alright, so those were properties. Looking at changes, this is the actual, the changing of the manipulation of that material. So physical changes change the visible appearance. So you manipulate what it looks like, but it stays the same thing. These can, and this is a huge thing students kind of miss a lot. They kind of probably mislearned this in junior high or their previous science classes. These can be reversible or irreversible. I can boil water. It's still water, whether it's in the liquid state or the gaseous state. And I can turn it back into water by condensing it. Whereas, if you cut your hair and get a bad haircut, that's irreversible. If someone takes a huge gouge out of the side of your head, that's irreversible. But it's still a physical change. It's still hair. It just looks bad. So reversible or irreversible, don't get that confused. Just because it's irreversible doesn't mean it's physical. You can have, or doesn't mean it's chemical. You can have physical changes that are irreversible. Your 6 phase changes, so sublimation, deposition, evaporation, condensation, melting, and freezing, those are physical changes. You can turn them back, so they are reversible, but the material stays the same is what matters. Whether it's water as a solid, liquid, or gas, it's all still water. We are not changing the material. Chemical changes, however, is where we make something new. So rust is not the same as that iron that was there before. When it rusts, it is not iron anymore. It's iron oxide. It's a different compound. That piece of paper we were talking about earlier, it's paper before, but afterwards it's carbon dioxide, water, and ash. It is a completely different substance. When things decompose or ferment, these are other just kind of good descriptors that show chemical change as well. You are making something new. This is actually out of the AP Chem textbook. I really like the story of this idea of acting upon or making something new. Especially down here, I drew my fingers across my trousers and discovered nitric acid acts upon trousers, just like it acts upon fingers. This is definitely a chemical change. That nitric acid is changing the cells in his skin. It's eating through his trousers. It is making something new. It is no longer the same stuff. So some signs of a chemical change. There are 6. You might see some other lists out there that say 5 or 7. I like 6. So one of them, gas production. Anytime something bubbles. So our Alka-Seltzer tablets or vinegar and baking soda, same thing. Precipitation. I'll have to show you one of these in class. It is not just rain or something like that. So precipitate formation is a sign of chemical change. Energy production, so light, sound, heat sometimes can be a sign of a chemical change. Heat's one you have to really watch. You have to look for maybe some of these other things to see if it really is chemical or not. But I have a bunch of demonstrations to show for you. Other one, so change in temperature, like we said, could be, could not be. That's the tricky one. 5, change in color. So think about a new penny versus an old penny. We call that patina. It's the same thing as rust, really, just with copper instead. And then the last one, an obvious change in chemical or physical property. So I like to use dog food here. The food before it goes in my dog looks a lot different and smells a lot different and probably tastes a lot different. I haven't tried before and after it enters the dog and exits, I guess. There's definitely an obvious change. It looks like this before, afterwards it's not so pretty. So obvious change in chemical or physical property is that 6th sign. To ask yourself, chemical and physical change. Is anything new being made? If you say yes, then it is chemical. If nothing new is being made, it just looks different, that's physical. So just some things to think about. Oops. So mixing salt and water, is that physical or chemical? In this case, it's just dissolving. And this is, again, another one of those things that people mess up a lot. If I just dissolve something, I'm not making anything. There's no chemical reaction going on. So dissolving, mixing, you hear words like that. Those are physical changes, not chemical. And then here, just another density question. Remember, density is grams over milliliters. So we can go through that one in class as well. The other thing then, types of matter. So hopefully this looks awfully familiar to you. That other stuff is hopefully review. But pure substances and mixtures. So our 2 types of matter. We can then subclassify them. So pure substances, you could either have an element or a compound. And mixtures, it could either be hetero or homogeneous. In terms of types of mixtures. So elements, simplest kind of matter. You cannot break these down any simpler and still have the properties there. So this is kind of our simplest, very basic level where if I have an element, it is all made up of the same type of an atom. So, and then your definition there, hopefully you know that. of atoms. Compounds, however, so it's still a pure substance. If you looked at every particle in that sample, it would all be the same thing. However, a compound is made by two or more elements combined. So that's when you probably saw this as being, or think of them as being touching. There is a chemical bond there. You can break these down into elements, but just think, if I have a sample of a compound, if I have water, every piece in there looks the exact same. It's two hydrogens and one oxygen bonded the exact same way. The other thing then, mixtures. So mixtures are physical blends of at least two substances. So again, this is a physical change when you mix things. But here they have variable composition, and every part keeps its own properties. So if something is heterogeneous, think of a chocolate chip cookie. If I look at the left half versus the right half, it's not identical. Even if you look at just one spot to another, one spot may have a chocolate chip, the other spot may not. It is not identical. It's not uniform. Same thing with like a salad. The tomato looks a lot different from the lettuce than from the onion, and from whatever else you have in there. So heterogeneous, hetero means different. It looks different throughout. Homogeneous then means same throughout. So if you look at Kool-Aid, you mix up some Kool-Aid. No matter if you're looking at the top of the container, the bottom of the container, the middle of the container, it looks the same, and that is homogeneous. We call these things solutions, so I will probably not use this word homogeneous a lot. I'll probably tend to use that word solutions. Not only limited to liquids, air around you, so what you're breathing right now is a solution. It's mostly nitrogen, a little oxygen, and then a little carbon dioxide and a bunch of other things. You can't spot the difference between the nitrogen and the oxygen and the carbon dioxide. It looks the same throughout. Salt water, when you mix it, same thing, like Kool-Aid there. It is a solution. Bunch of other stuff. The reason why these look the same is because it's mixed at such a small level, you just can't tell the difference. Again, can occur between really any state of matter. You could have like solids and solids. If you play baseball or softball, and an aluminum bat is not just pure aluminum, it's an alloy. It has zinc in there, it has chromium in there, it has a bunch of other metals that make them stronger or allow it to flex and stuff like that. Those are two solids mixed together, which we would call an alloy. So not just limited to solids and liquids like we usually think of them as. Most common solutions consist of one or more substances dissolved. So this is where we call solute and solvent. Don't worry too much about those words. We'll get way more into that later on this year. Same thing with this aqueous solution stuff. I just figured I'd throw it in. The cool thing is a true solution will never separate out or settle on its own. Where I first taught, there was a test tube of Kool-Aid that every August 26th was its birthday. And the first year I taught there, it was 19 years old. So now it would be like 24 years old. And I guarantee you to this day, it still looks the exact same. There's no separation. It's still the same color at the top, the middle, and the bottom as the day it was made. And we will stop there.